Hello everyone, we are Team JDI. Our project focuses on a simple question. In the age of attention, does a transformer really outperform a plain LSTM? To answer this question, we compared the two models on AG News under a matched parameter budget. We train both models from scratch and evaluate them under the same experimental conditions. In this presentation, we will describe our setup, present the results, and discuss several robustness checks. Let me begin with the motivation. Today, many people assume that attention outperforms rigorance. However, most evidence comes from large pre-trained models and wrong documents. Aging news is quite different. The headlines are short and the models are trained entirely from scratch. So we ask three questions. Which model performs better? How does the gap change with more data? And where do the two models differ in their behavior and errors? AG News is a balanced four-class news classification dataset. The most important feature is its short length. The average headline contains only 37 tokens. Almost all headlines fit within our 128 token limit. This creates a short context setting where the benefits of self-attention may be less important. That makes AG News a useful benchmark for this comparison. Now let's look at the models. The key idea here is fairness. The two models share the same embedding, pooling method, classifier, and training setup. The only meaningful difference is the encoder. One uses an LSTM and the other uses a transformer. Their parameter counts are also very similar. So any performance difference is likely to come from the architecture itself. For the result, let me briefly explain the protocol. Both models use the same pre-processing training pipeline and evaluation code. We run each experiment with three random seeds and report average performance. We also perform several robustness checks, including data scaling, length analysis, calibration, and design choices. The goal is simple: test whether the conclusion remains consistent. This is our main result. The LSTM outperforms the transformer by about 1 microampere point. More importantly, this pattern is consistent. As shown in the bar chart, the LSTM wins on all three random seeds. The paired t-test also shows that the difference is statistically significant, so the result is not driven by one lucky run. We also tested a larger bidirectional LSTM as a control. It performs only slightly better than the original LSTM, even with more parameters. This suggests that model size alone does not explain the gap. Overall, the recurrent encoder appears to be a better fit for this short text classification setting. The training curves help explain what we observe in the final results. The LSTM learns faster in the early stages of training. Its training loss drops quickly and remains consistently lower than the transformers. However, the validation loss starts to rise after the middle epochs, which suggests mild overfitting. The transformer shows a different pattern. It runs more slowly, but its validation performance continues to improve throughout training. This is why checkpoint selection is important. Rather than comparing the models at the same epoch, we select each model at its best validation macro at 1. For the LSTM, that occurs around epoch 8. For the transformer, it occurs at the final epoch. This ensures that both architectures are evaluated at their strongest point. Even after selecting the best checkpoint for each model, the LSTM still achieves the better final result. Next, we tested how the models scale with more training data. Our original hypothesis was that the transformer would benefit more from additional data. If that were true, the performance gap should decrease as we increase the dataset size. But that is not what we observed. The LSTM is already ahead at 25% of the data. More importantly, the gap becomes larger as we add more data. At the full dataset, the LSTM achieves its largest advantage. So the hypothesis is rejected. Within this data budget, additional data helps the LSTM at least as much as the transformer. The expected crossover never appears. This suggests that a transformer trained from scratch may need much more data or pre-training before its advantage become visible. Finally, we asked whether any single factor could explain the performance gap. To answer that question, we ran four robustness checks. First, headline length. The transformer shows higher error lengths across all length ranges, including the longest headlines. So the gap cannot be explained by sequence length. Second, calibration. This is the transformer's one clear advantage. Its confidence estimates are slightly better calibrated than the LSTM's. Third, pooling. We found that mean pooling performs better than a CLS token. This confirms that our original pooling choice was already a strong one. And fourth, learning rate warm up. Warm up produces almost no improvement and does not reduce the gap. Taken together, these checks all point to the same conclusion. The LSTM remains ahead regardless of length, pooling strategy, or training schedule. The transformer's only consistent advantage is slightly better calibration. Finally, we looked at the failure cases. The first thing to notice is that the LSTM performs better on all four classes. So the overall gap is not driven by a single category. Sports is the easiest class for both models, while business is the most challenging. The most common confusion is between business and SCI tech. Many headlines contain both financial and technical information. A technology company IPO is a good example. Depending on the wording, it can reasonably look like either class. We also compare the mistakes made by each model. A large number of errors are shared by both models, which suggests genuinely difficult examples. However, the transformer produces noticeably more model-specific errors than the LSTM. This means the LSTM not only achieves higher accuracy, but also makes fewer unique mistakes. Overall, the failure analysis is consistent with the earlier results. The LSTM performs more reliable across classes and performs better on ambiguous headlines. To conclude, our answer to the original question is clear. On short AG news headlines, a parameter matched LSTM outperforms a transformer trained from scratch. The advantage is consistent. The LSTM wins on every random seed, every rank range, and every class. We also tested several alternative explanations, including data scale, calibration, pooling, and warm-up. None of them changed the conclusion. One important lesson from this project is that fair comparisons require careful experimental control. Another is that from scratch, transformers appear to be much more data hungry than LSTMs in this setting. Looking ahead, the most interesting next step is to repeat this comparison with pre-trained transformers such as BERTs. It would also be valuable to evaluate longer documents where attention is expected to provide a larger advantage. Thank you for listening.